All right, so let's take a look at doing some just basic integrals. So let's take a look at, for example, taking the integral of, let's say, x to the fifth. All right, so if we want to take the antiderivative of this function, what we have to do is that we have to look at the power, and what we're going to do is that we're going to add 1 to that power, so that's going to become x to the 5 plus 1, and then divide by that new power, so divide by 5 plus 1. And again, we don't ever want to forget that plus c because that's that constant, so this is a whole group of functions. So our final solution will be x to the 6th divided by 6 plus c. Now let's say that we want to check our work and make sure that we got the right antiderivative. What we can do is that we can take the derivative of this function, so that's going to be x to the 6th divided by 6 plus c. Now remember that 6 is just a constant, so that's just going to stay there. So that's going to be 6 times x to the 5th divided by 6, whoops, 6. And remember, the derivative of a constant is just 0. These 6's are going to cancel out, and we are going to get x to the 5th, just like we thought we would. Awesome. Let's try another example, maybe one that's a little bit more complicated. So let's try an example where we have, let's say we have the integral of 4 times x to the 3 halves dx. All right, so by our derivative rules, what we can do with this constant out in front, because this looks like some constant times our function, is that we can take this constant and move it out in front. So we said that we could take that constant and move it out in front and just worry about the antiderivative of the original function. There we go, dx. So we can take that 4 and we can move it out in front and then just worry about taking the antiderivative of x to the 3 halves dx. Okay, now when we do that, we are going to get 4 times, now the antiderivative of x to the 3 halves, remember we're going to take x to the, add 1 to that exponent, so it would be 5 halves, divided by your new exponent, which is 5 halves, and don't forget, we always need to add that plus c. So I can simplify this out a little bit, so if you're dividing by 5 halves, that's the same as multiplying by 2/5 times 4 x to the 5 halves plus c, which is going to give us 8/5 times x to the 5 halves plus c. Now, just like last time, let's go ahead and check our work. So I'm going to check our work over here. So let's take the derivative of 8/5 times x to the 5 halves. Oh, you know what? I forgot plus c. So if I take the derivative of this, that's going to be 8/5. Remember, constants just hang out in front. Times, that's going to be 5 halves, x to the 3 halves. And again, the derivative of a constant is just 0. So those 5's are going to cancel out. I'm going to have 8 divided by 2, which is going to give me 4. X to the 3 halves. Look at us. We're amazing. We did such an awesome job. All right, now let's look at another example. Let's change it back to the blue. So another example, let's say that we're taking the integral of, let's say x to the negative 3rd power divided by 4 dx. So remember, dividing something by a constant, that's the same as multiplying by 1 over that constant. So that's the same as multiplying by 1/4. So x to the negative 3 dx. So it would be 1/4. Remember, we need to add 1 to that exponent, so that's going to be x to the negative 2. All of that divided by our new exponent plus c. So that would be negative, that's that negative right there, x to the negative 2 power divided by 8 plus c, which if you wanted to rewrite it, remember you don't have to, but you can if you want, that would be negative 1 divided by 8 x squared plus c. The reason that we can put that x squared in the denominator is because remember, when you have something raised to a negative exponent, you can put it down there. All right, that is looking so good. Let's look at doing another one. So let's do one that maybe is a little bit more complicated. So let's look at doing, for example, let's do the integral of the square root of x plus 17, all of that divided by x. All right, so let's get started on this one. Well, we'll do x to the third power dx. Now, the issue that I'm having with this, just right out the gate, is I didn't talk about what to do if I'm dividing two things. But that's okay, never fear, because we had this neat technique that said if I had a plus b over c, I can split that up into a over c plus b over c. I think that has to be like one of my favorite techniques to use. So if we use this technique, we can break this up into the integral, and I'm going to rewrite this as x to the 1/2 divided by x to the third plus 17 divided by x to the third dx, which I can rewrite even further. So if I'm dividing two bases, what I can do with their exponents is I can subtract them. So that's going to be x to the, well, 1/2 minus 3, that's going to give me negative 5 halves, plus, and what this is going to turn into is 17x to the negative 3 dx. Now there is an integral rule that said if I was taking the integrand of two functions being added together, I can just take the integrand of each of them individually. Remember, integrand, that's the same thing as antiderivative. So the antiderivative of x to the negative 5 halves, we'll have to add 1 to that. So that antiderivative is going to be x to the, well, negative 5 halves plus 1. That's going to give me negative 3 halves. Don't forget to divide by your new exponent. Plus, that's going to be 17, remember the constant just hangs out, times x to the negative 2 divided by negative 2. And we can just add c to this whole thing. If you took the antiderivative of each piece, both of them would have a constant. And remember, a constant plus a constant just gives you a good old constant. All right, so that would be our final answer for this one. Let's do one more example. So let's say I want to look at, say I want to look at the antiderivative of x to the negative first dx. Using our derivative rules that we just did, that's going to be x to the 0 divided by, oh no, we're not allowed to divide by 0. So a little note is that you can only use this antiderivative rule, n plus 1, only if n does not equal negative 1. The reason is that the antiderivative of 1 over x is the natural log of the absolute value of x. We know that because when we looked at taking the derivative of logs, we found out that the natural log had this very special antiderivative. So don't forget this property as we move through looking at logs. Okay, we have one more example to do, and then we're going to call it the end of the video. So, well, we'll do two more. So another example of taking the derivative, or I'm sorry, the antiderivative is, let's say that we had 4x plus 5 squared dx. Now we can't do the chain rule or the power rule because we have that 2 here, and remember we're doing the antiderivative. So what we need to do before we start taking the antiderivative of this is that we need to expand this portion first. So if we expand that out, what we're going to get is we're going to get 16x squared plus, so let's see, that's going to be 40x plus 25 dx. Now what we can do is that we can integrate each piece of this. So let's see, this piece here, that's going to be 16x to the third divided by 3 plus 40x squared divided by 2 plus, now this is just 25, but remember, if we were to take the derivative of, say, 25x, it would be 25. So whenever we have a constant like that, we're just going to tag an x onto it. So that's going to be 25x plus c. Now, just like last time, let's check our work by taking the derivative of this. So we're going to have 16x to the third divided by 3 plus 40x squared divided by 2 plus 25x plus c, and let's find the derivative. So let's see, that's going to be 16 thirds times 3x squared plus, that's going to be 40 divided by 2 times 2x plus 25 plus 0. Now these 3's are going to cancel out, the 2's are going to cancel out, so we're going to be left with 16x squared plus 40x plus 25, and that is exactly what we wanted. So we did, again, an amazing job. All right, for the last example, what we're going to be doing is we're going to be looking at marginal revenue. So say a company knows that their marginal revenue is MR of X, and let's say that it's let's say that they know that it's 400 plus 0.2x, and what we want to do is we want to find the total revenue. That is to say that we want to find R of X. So to find R of X, what we need to do is that we need to, well, this is the derivative of R of X, so we need to undo the derivative, aka antiderivative. So we need to take the antiderivative of our marginal revenue function. So if we take the antiderivative, anytime I take the antiderivative of a constant, it's just going to be that constant times x plus 0.2 x squared divided by 2 plus c. So our revenue function would be 400x plus 0.2x squared divided by 2 plus some constant c. Now let's say that instead of being given the revenue function, we were given the marginal cost function and asked to find the cost. We would do the same thing. We would take the antiderivative of that function.